Welcome to AminAcademy.com. In mathematics, we will discuss about Fourier coefficients in Fourier series. Fourier series of a periodic waveform is an infinite sum of sine and cosine waveforms where the frequency of each wave, sine and cosine, is an integral multiple of the period of waveform's fundamental frequency. Without any mathematical analysis, this statement might sound ridiculous. Why are we turning a simple waveform into a complex combination of trigonometric functions? Actually, the resulting Fourier series simplifies the process of signal analysis of the main function of our waveform at different frequencies. We can derive Fourier series for any periodic or continuous function or function with discontinuous values of its derivatives. Before processing figures, we need to understand the basic terminology we mentioned earlier, the periodic function. What is periodic function? A function f of x is periodic if for a constant t is greater than 0, f of x plus t is equal to f of x. Here t is known as the period of the function. Therefore, periodic function generally you can write f of x plus t equal to f of x where t is greater than 0. Here it's continuous, like that is f of x equal f of x plus 2t, f of x plus 3t equal, it's continuous. Is the period of function f of x. The function f of x repeats itself after equal intervals. Trigonometric functions such as sine x, cos x, tan x, etc. are some simple example of periodic functions. Now coming back to the Fourier series, if f of x is a periodic function, then we can express it as an infinite sum of the sine and cosine function as follows. Look at here. F of x is equal a0 over 2 plus a1 cos x plus a2 cos 2x plus a3 cos 3x plus dot dot dot, that is an sin cos nx plus b1 sin x plus b2 sin 2x, b3 sin x, that's continuous, bn sin nx. Here, therefore, f of x is generally in sigma form. We can write a0 by 2 plus sigma n equal to 1 to infinity an cos nx plus bn sin nx is the Fourier function. That is, Fourier series in general form is like. Here a0, an, bn are known as Fourier coefficients. The value of these coefficients are what define the Fourier series of a function. Constant a0 is the average value of the periodic function. A0 is the average value of the periodic function, and an and bn are the amplitude of the various sinusoidal functions. Here a0 is the average value of the periodic function, while an and bn are the amplitude of the sinusoidal functions. We can calculate a0, an, bn using the following expression. For example, if f of x is a periodic function, then Fourier coefficients of its Fourier series in the interval x is greater or equal to t and lesser or equal to t plus 2 pi are as follows. Here, the coefficients of that Fourier series is a0 is equal 1 over pi integral t to t plus 2 pi plus f of x into integral of f of x dx. An is 1 over pi t integral t to t plus 2 pi f of x cos nx dx. Then bn is 1 over pi integral t to t plus 2 pi f of x sin nx. These are important facts of the coefficients. The equations a0, an, bn are known as Euler's formula. Here, this formula, that is a0 is here, an, bn are called Euler's formula for the coefficient of Fourier series. In the previous Fourier series equation, we used both sine and cosine functions but we can further modify the equation to give an equation only in terms of sinusoids. Without cos also I can write. We have the terms an cos x plus bn sin nx, that is an cos nx plus bn sin nx. In the equation we can rewrite the following as an cos nx plus bn sin nx equal to an sin nx plus 90. That means instead of cos we can write cofunction, that is an. Look at here, this instead of cos nx we are writing here an sin nx plus 90 with bn sin nx here, which is equal cn sin of nx plus theta n. This combined together we can write this is cn sin of nx plus theta n, where cn is square root of an square plus modulus an square plus bn square, and theta is tan inverse an by bn. Using these terms we can derive the sinusoidal only Fourier series expression as follows. Now look at here, f of x equal to a0 by 2 plus cn sin of x plus theta 1 and here f of x equal a0 over 2 c1 sin of x plus theta 1 plus c2 sin of 2x plus theta 2 c3 sin of 3x plus theta 3, like it goes. In general you can write f of x equal a0 by 2 sigma form, sigma n equal to 0 to infinity cn into sin of nx plus theta n. This is a sinusoidal function for Fourier series. There is no cos function. We combine cos in terms of sine. In the above equation, notice that n equal to 1, the sinusoidal quantity has the same frequency as the main function, which is x in this case, and it is the fundamental frequency of the main waveform. All the subsequent frequencies like n equal to 2, n equal to 3 and so on are integral multiple of this fundamental frequency, which we call as harmonic frequencies. So for n equal to 2, the frequency of the corresponding sinusoidal is known as second harmonic. Similarly, n equal to 3, the third harmonic, n equal to 4 is the fourth harmonic, n equal to n, that is nth harmonic, we can write. Now, derivation of Fourier coefficients. Now, we'll discuss further about how to derive the coefficient of Fourier coefficients in terms of other functions. From the above discussion, it is clear that the Fourier coefficients a0, an, bn and bn are the critical value that we need to calculate for any Fourier series. We have already seen the expression for these constants, but let us try to derive them. For this, let us assume that f of x is a periodic function and its Fourier series for the interval t, t plus 2 pi, that is x is greater or equal to t and lesser or equal to t plus 2 pi is given by, look at here, f of x equal to a0 by 2 plus n, sigma n equal to 1 to infinity an cos nx plus sigma n equal to 1 to infinity bn sin nx. So this is the periodic function and its Fourier series with interval of this is here. Now, how to express coefficient a0, an and bn now. Expression for a0. In the above equation, let us integrate both sides from x equal to t to x equal to t to 2 pi. We get, look at here, integral t to t plus 2 pi f of x dx equal a0 over 2 integral t to t plus 2 pi with dx, that is it into 1 plus sigma n equal to 1 to infinity of integral of an integral t to t plus 2 pi cos of nx dx plus bn into integral t plus 2 pi sin nx dx. That is, we are integrating separate and add together. So here a0 to that is integral of dx with respect to t to 2 pi is 1 into t plus 2 pi minus t. So t cut, this 2 pi come, plus integral sigma n equal to 1 to infinity an integral of cos x, we know that sin nx over n integral t to t plus 2 pi plus bn integral of sin nx, we know that it is minus cos nx over n t to t plus 2 pi. Here we simplify this. This is a0 by 2 t and t cut 2 pi, then 2 and 2 cut, this is a0 pi plus sigma n equal to 1 to infinity. Look at here, if you are using the limits t plus 2 pi to t plus 2 pi and simplifying, which this is 0, this part also 0, we have a0 an into 0 bn into 0, that is we have that is equal to a0 pi, that is here expression for a0 pi is a0 is a0 pi. From the above equation we can get the expression for a0 as a0 equal 1 by 2 pi a0 equal to 1 by 2 pi integral t to t plus 2 pi f of x dx. Now expression for an. Now we'll express an in terms of simplification. Now consider the original Fourier series expression. Once again multiply both sides by cos mx and integrate the resulting equation from x equal to x equal to t plus 2 pi. We have integral t to t plus 2 pi f of x cos mx dx is equal to a0 by 2 integral t to t plus 2 pi cos mx dx plus integral that is sigma n equal to 1 to infinity an of this integral and add, that is integral t to t plus 2 pi cos nx cos mx plus n equal to 1 to infinity bn t to t plus 2 pi sin nx into cos mx dx. We have in the above expression, if you observe closely, the integrals corresponding to a0 and bn, first and third are always 0, coming to the second integral corresponding to an for all m is not equal to n, the cases we have like becomes 0 and the only possible outcome is for m equal to n, therefore which is equal integral t to t plus 2 pi f of x cos nx dx equal to half integral n equal to 1 to infinity an integral t to t plus 2 pi 2 cos square nx dx. That means the simplification of integral this and this becomes like 2 cos square nx dx, which is equal an by 2 take out of the integration t to t plus 2 pi 2 cos square nx, we know that 1 plus cos 2 nx dx. This is trigonometric formula of identity of 2 cos square nx equal 1 plus cos 2 nx. So an by 2 integral of 1 is x, integral of cos nx equal to sin 2 nx by 2n, limits is t to t plus 2 pi. So for the simplification we have, after substituting the value of t plus 2 pi and t for x, we have an by 2 pi, which is equal to an pi. For the above equation we get the expression for an as an is 1 by pi integral t to 2 pi f of x cos nx dx. Expression for bn, similarly like for bn we have. Now consider the original series expression once again, multiply both sides by sin mx and integrate at the resulting equation from x equal t to x equal t to 2 pi, t plus 2 pi we have integral t to t plus 2 pi f of x sin mx dx equal a0 by 2 integral t to t plus 2 pi sin mx dx is plus n equal to 1 to infinity an integral t to t plus 2 pi cos nx sin mx. Similarly for integral bn into the same things. In the above expression, integral correspond to a0 and an, first and second are always 0. Coming to the third integral corresponding to bn for all m is not equal to 0 cases becomes 0, and only possible outcome for value m equal to n only. So similarly like before, integral t to t plus 2 pi f of x sin nx dx equal half of integral n equal to 1 to infinity to bn integral t to t plus 2 pi to sine square nx. That this function that is cos nx into sin nx is 2 sine square nx, which is equal bn by 2 integral t to t plus 2 pi. We know that cos 2 sine square nx is 1 minus cos 2 nx dx. So integrating separately, integration of 1 is x, integral of minus cos 2 nx is sine minus 2 sine nx by 2n. Substituting the limits t plus 2 pi and t, we have bn by 2 is 2 pi because this become 0. From the above equation, we can get the expression for bn is 1 by pi integral t to t plus 2 pi f of x sin nx dx. Therefore, in generally, with Dirichlet formulated sufficient condition that a periodic function, we can express any function f of x in Fourier function as f of x equal to a0 by 2 plus integral with sigma n equal to 1 to infinity an cos nx plus sigma n equal to 1 to infinity bn sin nx, where a0, an and bn are constants of the following sufficient conditions are satisfied. The function f of x is a periodic, single valued, well defined and finite function. It is a finite number of discontinuities in any periods. F of x has finite number of maxima and minima in a bounded interval. When these conditions are met, then we can obtain the Fourier series for any functions. Assume the generic form of series with respect to the function as follows. Here f of x is a0 by 2 plus sigma n equal to 1 to infinity an cos n pi plus sigma n equal to 1 to infinity bn sin nx. Calculate the value of the function of the formula. A0 is here and an is here and bn is here. We derived before. Now some applications. The concept of representing any waveform or function purely in terms of the sinusoidal waves, Fourier series and Fourier transform, which together form a new set of mathematical solution of partial differential equations, signal processing, statistics, seismography, oceanography, etc. Conclusion, we can write this was an introductory guide for Fourier series. Further, we will discuss in further videos some example formulas for Fourier series. We have done. Please subscribe our YouTube channel.